Swayam Prabha. Digital India. Educated India.
So, good morning everyone. So, last class we saw this theorem, we understood what this theorem is saying us. So, what it says us is that suppose if we have a function over some variable set, and if I consider disjoint subset of that variable set, let us say disjoint subset y1 to ym, and now suppose I look at the number of sub functions. So, let Si be the number of sub functions of S f on yi. Okay. So, basically the number of distinct sub function were restricted to yi. Okay. So, then the number of leaves of this function f, I mean the formula size of this function f over B2 is greater than or equal to 1/4 log of Si. Okay. So, this is what we saw last time, and the way the proof works is basically we count the number of leaves. So, we show that basically for one second, this is not correct. So, this will be 1/4 sigma I equal to 1 to m log of Si. Okay. So, what we show is that the number of leaves. So, if I look at a sub function Si, then the number of leaves, the number of ways of counting all the trees that are possible is greater than or equal to 1/4. Huh? 1 plus, no, the 1 should be on the left hand side. So, it is greater than or equal to this minus 1. So, did I write it 1 on the right hand side? Oh no, it should be the other way around, sorry. Yeah, so it is greater than or equal to this minus 1. Okay. Okay, so we saw this, and then I mean, so what is the idea? So, before this we saw Kravchenko's theorem. So, in Kravchenko's theorem also we gave a lower bound on the formula size, but that was over the De Morgan's basis, right. So, here we are giving a lower bound on the formula size, but this is over the basis B2. Okay. Okay, so how can we apply this theorem? Okay. So, let us consider a function as follows. Okay. So, application. So, consider the following problem. It's called, it's also known as the element distinctness function. Okay. So, we will define this function, we will see what this function does, and then we will try to construct a lower bound using this theorem. Okay. So, what is this function? So, this is a function, let us call it ED from 0 1 to the power n to 0 1. So, essentially, okay, so before I give the full definition of this function, let me just kind of say what this means. So, the domain of this function encodes m integers, okay, m positive integers, and the function would evaluate to 1 if all the integers are pairwise distinct. Okay. So, basically no two integers are exactly the same, okay, otherwise it evaluates to 0. So, that is the idea of this function. So, how do we define this? So, where n equals to 2m, the ceiling of log m, okay. For some m, and anything else? Yeah. So, we view the input as m blocks of size 2 log m each, and each block is a, let us say, positive integer. Okay. So, each block encodes an integer. Okay. So, basically each block would encode an integer between 1 and m square, because using 2 log m blocks you can have an integer as large as 2 to the power 2 log m, which is m square. Okay. So, in some sense the domain can take any value, I mean the domain can take m integers, where each integer is something between 1 and m square. Okay. Now, yeah, so now I will define how the output is, how we define this function. Now, EDN of x1 to xn is equal to 1 if the m blocks are pairwise distinct okay, and it is equal to 0 otherwise. So, if no two of these numbers are the same, then we define that function to be 1 and it is equal to 0 otherwise. Each block is of size 2 m log m, sorry, each block is of same 2 log m. Okay. So, let us look at it pictorially. So, I have first block is x1 up to x 2 log m. Okay. Then, so this is block 1, then I have x 2 log m plus 1 up to x 4 log m, okay, and so on.
Here if x1 to x2 log m are all 0 and x2 log m plus 1 to x4 log m is also 0, then the output will be 0.
Yes.
But if they are different, then like if all pairs are different,
Then it is 1. Okay. Up to x 2 m log n. Okay. So, now what can we say about the formula size of this function? What can we say about the complexity of this function? Okay. So, the question is if we want to use Nechiporak's theorem to give a lower bound, then we have to define what these disjoint subsets are going to be. Okay, we have to define what these disjoint subsets are going to be. Then we have to understand for each subset, if I restrict the function to that subset, how many distinct subfunctions are possible, and once we get a value of that count, by the theorem we will get a lower bound. Okay. So, what will be our subfunctions, what will be our subsets? So, consider, so we let yi, okay, be the set of variables let us not call it I, let me call it yj, be the set of variables x j minus 1 times two log m plus 1 up to x j times 2 log m for j between 1 to m. Okay, let us just check if I wrote this correctly. So, take j equal to 1. So, when j is equal to 1, this is 0. So, it starts at x 1 and goes up to x 2 log m, right. When j equal to 2, it starts at 2 log m plus 1 and goes up to 4 log m and so on, and when j is equal to m, it goes up to m log m, correct. Okay, so, these are the each of my yj's. Now, for each yj, how many distinct subfunctions are there, okay, for this function. So, this is basically the crux of understanding this problem. So, what do we mean by a subfunction here? Okay, so, the subfunction means that, well, only that particular yj. So, let us take any yj. Okay. So, only that yj is allowed to take different values and the rest of all the variables are fixed, right. What does that mean? So, first of all, so before getting into that, let me just write this. So, the number of possible values using 2 log m bits is m square. Okay, so, this I already said this, that each of these blocks can take m square different values, right. Now, when I fix m minus 1 blocks and only one block is allowed to take different values, what are the various choices for which this subfunction evaluates to 1, or how many different such subfunctions are possible, right. So, how many different values can this yj take? So, suppose let us say we consider a block yj, okay. How many different values can that yj take? 2 to the power 2 log n. So, basically it can take m square many values, right. So, it can take m square many values. Out of these m square many values, how many values will set it to 0? Okay. So, basically when I am looking at these m square many possibilities, the remaining m minus 1 yj's, they are already fixed. Okay. So, this yj now can take any of the other m square minus m minus 1 values, okay, for any of the others. So, there are m minus 1 ways. So, basically m square minus m minus 1 is the same as m square m minus 1, it is the same thing. So, this is the total number of subfunctions that are possible for S, let us say j over here. Okay. Actually, it is. So, for each of these I get a different subfunction. So, the number of subfunction is actually greater than or Sj is. So, for each of these I have a subfunction yeah. So, the number of subfunction is upper bounded by this quantity. Okay. Now, what is this? So, this is I can use Uh, huh? No, for each of these I have a subfunction. Sorry. Huh?
Each of those will be distinct. If there is one more function which comes from, for instance, two of the other blocks are the same, so then that will be a constant zero function.
So, I have m minus 1 values for the other m minus 1 yj's, right. So, this is the total number of ways in which I can choose different functions over yj, right. So, what are you saying?
I'm saying that once we, so one or any function and another function comes from picking any two of the remaining blocks to be identical, and that gives you
So, it is basically, it can be something more, I mean the, okay. So, what you are saying is,
we need a low bound anyway for applying.
right, right. So, one second, you are right, yeah, yeah, correct. So, you will actually have other things also, like when, if let us say two of those some other blocks have the same number, yeah, that was incorrect. Yeah, this is actually a lower bound on the number of functions, yeah. So, now you can apply, okay. So, how do we get a bound on this? So, we apply this m square minus m plus 1 whole to the power m minus 1, right. So, this gives us a bound on S j, and so therefore, log of S j will be greater than m minus 1 times log of m square minus m plus 1, and this is, yeah, we actually need a lower bound over here. So, this is omega of, so here I have an m term and this is a log m term. So, I have m some for some constant, it is greater than that constant times m log m. So, the extra things are, so basically what I am trying to do here is, for each subfunction, what I showed, what I argued over here is that for each subfunction, this is a way in which I can choose something, right. But now what can happen is, let us say that if I look at these blocks, okay. So, I have these blocks 1, 2, and then I have the jth block, and then I have these other blocks. So, here I am counting that if I have different values for all these other m minus 1 blocks, what value can the j block take, right. But also what can happen in addition to that is that some of these blocks can have the same value, right. Maybe two of these blocks can have the same value, okay. So, basically S j will have, I mean there are more number of subfunctions possible than this quantity, okay. So, if two of these blocks have the same value, then I have to choose from m minus 2 different numbers, m square choose m minus 2, something like that. I mean there will be some more quantity, right. Maybe 3 of those blocks have the same value. Yeah, but so what I am saying is that, so if 2 of those blocks or 3 of those blocks have the same value, then basically it is a function which is going to 0 still, okay. But there are more ways in which that can happen. But that is still a sub function, okay. It is a sub function which is going to 0, So, we have this bound. So, now so this is in terms of m, and what we have is what is m? We have n equal to 2m log m. Okay. Therefore, if I take m log okay, that is fine. Therefore, this is equal to omega n, right. Okay. Now, let us look at this application of this theorem. So, now by this theorem, what we get is L B2 of f plus 1 is greater than 1/4 sigma log of Si, which means that it is I going from 1 to m, which means that this is greater than m times n. So, how can I write m in terms of n? So, essentially what we will show is that m is greater than n by log n. So, this is what we want to show. Okay. So, let us see. So, if I take log on both sides, what I get is log of m greater than log n minus log n, and if I substitute this over here, huh? Log n only I wrote. No, here I want to show this is n by log n. Yeah, I am just trying to back calculate and see for what essentially I want to show that m is greater than n by log n. So, I am just trying to back calculate and trying to see that if I make this assumption, does it still fit this theorem. Okay. So, this can be done in a better way. Okay. So, what do we have here? So, we have 2m log m. So, if I assume this, then this quantity is greater than n by log n times twice n by log n times log n minus log n. So, this is equal to 2n minus one minus log n by log n. So, this is less than 1. So, this is greater than n actually. So, yeah, okay. So, basically if I assume m to be greater than n by log n, then this actually holds. Okay. So, m is omega of n log n. Okay. So, this works out. So, therefore, I can write this as equal to omega n square by log n. Okay. Now, this is a lower bound that we get using this theorem. Now, what can we say about an upper bound on this function, element distinguished function? In other words, can I construct a formula for this function? Okay. So, what we will show is that this bound is actually a tight bound. In other words, we can actually construct a formula which has the same size. Okay. So, this is actually quite easier to see. So, consider this function. So, first I will define a function, let me call it same I comma j. Okay. So, what this same I comma j is that it takes the input and this function evaluates to 1 if the ith and the jth block are the same. Okay. So, same I comma j on x1 up to xn will evaluate to 1 if ith and jth block are the same, and this will be equal to 0 otherwise. So, how can we define this function? So, I can define same I comma j as AND of. So, basically if I look at these two blocks, so when I what do I mean when I say that these two blocks will be the same? It means that each and every bit in those two blocks have to be the same. So, the ith block is from x I minus 1 times 2 log m plus 1 plus, let me write it as plus k, okay, where k goes from 1 up to so each block will have 2 log m elements up to 2 log m. Once again, let me just rewrite this. So it is I minus 1 times 2 log m plus k is equivalent to x j minus 1 times 2 log m plus k. Okay. And what do I mean by this equivalent sign? It means that if both these bits are 1, then the function evaluates to 1. If both these bits are 1 or both those bits are 0, then the function evaluates to 1, otherwise it evaluates to 0. Okay. And this can be actually done using a constant formula. Okay. So, this is basically can be done using a formula of size whatever 3 or 4 size. So, the size of, okay, So, we have this same ij. Now, how can I write Ed in terms of same ij? How do I write Ed? So, Ed says that all the blocks should be pairwise distinct. Same ij is saying that for two blocks I and j, they are exactly the same. How can I write Ed? So, what happens if I take a disjunction of all the same ij's for every pair ij? What does that function mean? What does this function mean? There exist two blocks which are equal, right. So, same ij means that I and j are equal, and then I am taking a OR over all the ij, which means that there exist two blocks which are equal. So, what is Ed then? It is just the negation of this. Ed says that there does not exist any two blocks which are equal, right. So, it is just the not of this entire thing, right. Now, what is the size of this construction? So, what was the size of same ij? The size of this one was order of, so I have m many ors over there. So, it is m times that is constant size. Okay. So, that was order m. And now, how many such ij's I have? I have a total of n square ij's. So, this part is order m square. So, I have a total of m square many such pairs, and this is a knot. Okay. So, this is equal to order of no, sorry, this is not m, this is log m, right. This is log m, and here I have m square, yeah. So, this is m square log m, and what we saw is that m log m is n and m is this thing. So, this is order of once again n square by log n. Okay. So, for this function we have a upper and a lower bound of n square by log n.